Okay, so we'll get going again. As with yesterday, I'll switch my video off in a minute so we don't have to consume bandwidth with that. And do let me know if you can't hear what I'm saying, or if it's not clear, or if I do need to repeat anything. And please do keep the questions coming like yesterday, because it was great. It's good to have the interaction on the course. I do miss it from face-to-face teaching, where you can see people in the room and get some good interactions going. So any questions you have, do throw them up or ask over the microphone, and we'll endeavour to answer them. So this is the last lecture session where I'm going to cover memory optimizations. In this lecture, and then straight after it, back-to-back vectorization. So this is sort of one long lecture. Memory optimizations is a little bit misnamed, so it's really just sort of programming efficiently for memory usage, and it comes back to some of the things you'll have seen this morning in the OpenMP stuff, so around the cache coherency and their false sharing and things like that. And you know, very much speaks to a piece around cache usage and memory hierarchies for good performance. And you know, the reality is, for a large percentage of computational simulation codes, or codes in general, getting memory to work efficiently is the best optimization you can do, and that's where most applications are bottlenecked. And it can be that for a lot of applications they really are memory bandwidth bound, which means that most of their performance is reliant on good memory usage, and if you can get the memory usage as good as possible, or get the cache usage as good as possible, then you can't do any better than that. So there's often no need to do any of the more complicated optimizations on the pipelining of instructions and these kind of things, because they don't generally benefit you, because really what you're doing is waiting for data to come in from memory, or you're using data as quickly as possible. And that's the limiting factor. Now, of course, there are caveats to that, and one of the big caveats to that is vectorization. And so even if you're memory bandwidth bound, making sure you use vector units and access data efficiently from those vector units is a beneficial thing to do on modern processors. So, so there's these two lectures which we'll go through. And it will probably take longer than you want and than I plan, but we'll go through them. And then the idea is to get into some practical. There are a number of practicals on the practical sheet you can go through, some explicit vectorization ones, and also some more involved optimization ones. And the idea is that there's an hour extra in the session, you know, today between now and the end of the course, for you to do those practicals and ask questions, but actually there's far more practical material than we can get through in that time. So you're free to do this in your own time, and as I say, we still have access to a system for a month after this course, so you can come back and revisit them. And the nice practical from my point of view is there's one called the molecular dynamics one, which you looked at a little bit for the OpenMP practicals this morning, I believe. And really, it's a code actually we use on our MSc here. I teach a course on our MSc here called Performance Optimization, and it's a code we use to give to the students to see how well they can optimize it. It's a code which is explicitly being made bad. So the performance is bad because it's been structured in such a way, and the makefile's been structured in such a way that it's very slow, and then students are asked to apply some of these optimization techniques to speed it up and see how fast you can go. And that's exactly the same as what you can do here. So that's quite a nice one to look at, where you can do the whole profile, optimize, and reprofile and cycle on an actual small application code. 1 second, I'll just tweak my audio setup, Helen, and see if that improves things for you. Louder, but if it's not, if I am quiet for people, do let me know. Good. Anyway, let's get on. You don't want to sit and listen to me all day. So as usual, this is material you can use and share if you like. So this first lecture is about memory, and hopefully by now we're all aware that memory performance is very important for applications. And so changing memory structures, or at least making sure you're programming in a memory efficient way, is one of the best things you can do for performance optimization. And the thing about memories, or memory usage or data structures, is of course there's no correct thing from a programming perspective. So you can write a program in such a way that it produces correct results, but its performance is very poor just because it doesn't match the memory hierarchy or memory structure that the hardware has. And we see this very often in computational simulation code, where you have multidimensional arrays and applications using those multidimensional arrays in perfectly legal, perfectly correct ways, but just poorly performing ways because the arrays are laid out in memory in a certain way, and the program iterates through those arrays in a different way. And that means you have many more cache misses, many more memory loads and stores than you would have if you did it in a way which is what we would call contiguous in memory. So memory structures are frequently global to the program. Communication between different parts of your program often happens through the memory structure. And what we mean here is that you pass a data structure into a function, it'll update that data structure, be it a linked list or a large array or something like that, and then it will return it, and another function will take that. And the programming cost of changing a memory structure can be very high as well. So that's always one to look out for, because if you've got to change how your memory structure is used, say you want to go from a linked list to an array or a matrix, that may be quite an extensive change to make throughout your program. So it's actually, if you're starting afresh with a new program, one of the best things you can do is spending a little bit of time getting your memory structure set up and designed and created in such a way that it's going to be efficient and easy to use. Is good use of your time. One of the main reasons that memory structures are so important for us in terms of performance is, of course, the compiler really can't do very much about them. You, the programmer, has told the compiler what the memory structure is. You've manually specified this in your application, and the compiler is really not free to go away and change it into a different kind of memory structure. The compiler has lots of latitude in things like reordering of instructions. So you've written a program and you say A equals B plus C, and then D equals Q plus R, and then F equals 1 plus 2. And as long as those things are not dependent on each other, actually, just because you put it in one order, you wrote it down in one order in the program, the compiler, once it's turned into instructions and passed the processor, those instructions can be done in any order, and the compiler and the processor can work on optimizing the order of those instructions to get the best performance. But if you give the compiler a program with a data structure in a linked list, it's not going to be it doesn't have the functionality or the latitude to take that program and change the linked list into an array, or change it into a set of individual variables or anything like that. Now, of course, there's some really nice research that can be done there in writing tools which can change data structures in programs, and mapping data structures to other data structures and things like that. But in general, this is not what a compiler will do. So if you can get a data structure which we use in a program, which is as efficient as possible, then that's going to help your whole program from a point of view. And so when we're talking about data structures, we're talking about things like arrays, pointers of arrays, records or structures, trees or lists, and objects. And it depends on the programming language you're using and the approach you're taking, what kind of data structures you use. And if you end up with something like a C++ program where you do an object-oriented programming, you'll have a class with objects, and those objects may have arrays or or trees or lists. So you'll have various of these throughout your program. Arrays or matrices, which are then translated into arrays, are sort of the most common data structure in high-performance computing codes or computational simulation codes and machine learning codes. And it's because these are really good for representing discrete versions of continuous data. So you can turn a function into a set of arrays, and each point in that array represents a discrete point on a continuous function. And of course, you can then represent data from the real world or from an experiment in that set of structure. So if we looked at this in Fortran or in C, we've got Fortran here at the top. Let me get my pointer. Fortran here at the top and C at the bottom. We can see we have, the language defines ways of or provides us ways of defining arrays. So in Fortran, we have these real A and brackets, and that will tell us an array. And in C, we have these square brackets to define the size of arrays. I'm assuming none of this is particularly earth-shattering to any of you who are attending the course, but I mean, these are pretty standard programming techniques for creating data structures in C and Fortran. And actually, both of these languages, and this is not true of all languages, but both of these languages support multi-dimensional arrays as default, as a sort of built-in structure in the language. Now, the multi-dimensional arrays we see down the bottom here, these two on the left here, these two definitions are generally really used for good, ease of understanding and ease of programming. So you are mapping your data structure to something which makes sense in your formulas or your physical problem or something like that. In reality, of course, there's no difference between this multi-dimensional array and this single-dimensional array in the amount of data that's stored. So a real array of 1 million elements is in memory pretty much equivalent to a real array of 100 times 100 times 100 elements, and I've probably got a 0 wrong there, right? That's probably 10 million elements, but excuse my poor counting. And in reality, what's going on under the hood is that if we have these static arrays where we have multi-dimensions and we're indexing like this, we can actually convert them into single-dimensional arrays where the indexing is done for us. And actually, this is slightly incorrect, isn't it? I'll fix it just now because that's nasty. The only problem with fixing it, of course, is it stops my sharing of the screen. There we go. So yeah, sorry, the brackets were wrong on this this one over here. The brackets were wrong. So you could write this all as single-dimensional arrays. And do the indexing into these arrays yourself. So this is equivalent to this over here, except this is just quite nasty and easy to make mistakes in. So actually, it's nice to prefer this method, multi-dimensional arrays. There is some address calculation required here, but it's exactly the same as the address calculation that's required over here. So you're not really saving anything in any one of these forms. Now, of course, this masks the fact that actually statically defined arrays are probably less useful for most programs because you have to define up front how much data storage you want, and that may vary from different input files for your applications. So in reality, most people will end up doing dynamic arrays, and we'll come on to look at those. But the important thing to understand about array accesses is the nice thing about it is that the data access pattern is regular and easy to predict. And if you do it right, you get good spatial locality. So you access neighboring elements of the array on consecutive iterations of a loop. So we can imagine here, And now this starts to get slightly complicated because C and Fortran do different things here, and this always becomes confusing moving between them. But we've got a multi-dimensional array here with 100 times 100 times 100 elements. And these are actually, what actually happens is these are stored in memory as chunks in contiguous space of 100, and then 100 of those, and then another, 100 of those chunks. So effectively what happens is this dimension here is the one that's contiguous in memory. What does that mean? It means that if you go to a spot in memory and then you move on to the next spot, say we're using floating point numbers here, floating point numbers, say 64-bit floating point numbers. So if we start at the beginning of array 0, 0, 0 in C, and then we moved on one element in this k dimension, that would just move to the next position immediately adjacent in memory by 64 bits, and likewise we keep moving on. And this is important to us, of course, because if we remember from what we talked about cache yesterday, and potentially what Mark talked about cache this morning, when we load data in from main memory onto a processor, we don't load it in individual bits or individual units of 64-bit units. We load it in cache lines, so maybe 128 bytes. And so actually when we load A000, we load A000, but because it's stored in memory in a certain way, the cache line will also contain A001 and A002 and A003 and A004, all the way up to 128 bytes, whatever that is in terms of a cache line. So that's 64-bit elements, that's 8 bytes, and then how many 8s are in 128 bytes? Probably 16 elements. So we probably load here A000 up to A0015 in that single cache line load. And you can see the nice thing about that, of course, is that if we iterate through correctly on this loop, when we go A001, 0, and then 01, and then 02, and 03, when we've done that first cache line miss and loaded the data in, then we've automatically got A001 and A002 in memory already, and 3 and 4. And so we don't have to do another cache miss and another cache miss for each element. We get all 16 at once. And that means we can do 16 operations for one load here. But that's assuming you're iterating through nicely, and this is your innermost dimension of your loop. I see there's a couple of questions in the chat. I'll come to them in 1 second. Just let me finish this bit here, which is the nasty thing, of course, is that Fortran does it the other way around. And so in Fortran, this element here, the first element in the dimension of the array, is the one that's stored contiguously in memory. So actually, you have to iterate through 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 1, 5, 1, 1, 6, 1, 1 to get all the elements of that cache line. But as long as you structure your loops correctly to do this, then you get your sort of most dense reuse of that data, that sort of temporal locality we were talking about. And this is an example. These are examples of this feature here. So, okay, there's a couple of questions. In the case where one does not know compile time or dimensions, but is able to decide an upper bound, would it make sense to have static days? Yes, so it's a perfectly acceptable programming technique to say, yeah, I know this array is only ever going to have 1 million elements, so I'm just going to make it 1 million elements long, but maybe I won't use all those 1 million elements for a given program. But the only place that falls down, of course, is if it uses more memory than you need, and if you've got a program with that needs a lot of memory, it can be, that your program fails to run because it needs too much memory. So as long as you are not ever going to be using more memory than you can fit in on the computer you're running on, that's perfectly fine. You can also recompile a program. You can have these things statically defined in compile time and then change them, recompile your program every time you run a new job. That's also perfectly fine. It just tends to be a little less user-friendly, and so people often end up using dynamic memory, which is not a problem. We'll come on to talk about it, but it does the compiler is more easily able to optimize statically defined things when it does dynamically defined things. Oh yeah, so it's a good question here. So A123 in Fortran is next to A124. In Fortran, no. So in C, A123 would be next to A124. In Fortran, A123 is next to A223 and A323. So it's just that different dimension. In reality, if either in Fortran or in C, A211 is nowhere near A124 in either of them, because in Fortran, let me just see if I can write this down. So in Fortran, A211 versus A124 in Fortran is, okay, so A224. So either way, if you're going to move in 2 dimensions, you're not going to be near each other, either in C or Fortran, right? So you're only ever contiguous in 1 dimension. So in C, what you could say is, in fact, I'll use a different computer, my other computer, to do this because it's going to be quicker for me to type. So in C, A000 is next to A001, but A010 is 100 elements away from. Apologies, I'm speaking whilst I'm typing, which is why it's slow. You'll be like my kids who are always frustrated with my messaging on the phone, which is always too slow for them. So, and 100 elements here, say 100 times 64 bits, or 800 bytes. So it's always going to be a cache line away. It's totally good questions. These are definitely good questions to ask, and good questions to get a handle on, because this is one of the most important things for computational simulation programs, to get it right. Now, actually, it could still be contiguous in memory, right? So A0099 could be exactly next to A010 in C. Those could be contiguous in memory. It's just A000 is a long way from A010. Now, but the way C does memory, there's nothing to say that A0099 is exactly next to A1010, because it can chunk up the dimensions, and there can be gaps between them if it wants. But in reality, as long as that innermost dimension, as long as the IJK dimension here is big enough that those gaps don't really matter to us. Now, of course, in Fortran, it's the other way around, right? So A111 is next to A211, but A111 is, this is where I miss a whiteboard, 100 elements away from A121. So in Fortran, and likewise, if you move, if you wanted to see A111 is 100 times 100 elements away from A112. So if you move the last dimension, you're even further away in memory. A111 is 100 times 100 elements away from A112. because of the way these data structures are. Are there any more questions about that? And we can go through this example here, if that's useful. Well, we'll go through this example here. So here we've got Fortran, and then we've got C, and again we've got Fortran C because they do different things. One's row major, one's column major. I can never remember which is which, but one, it's the last dimension, which is contiguous in memory, and that's C, and in Fortran it's the first dimension, which is contiguous in memory. And so we can see that it's important here for these loops. Now, if you've got a single dimensional array, single dimension loop, you don't need to worry because it's all the same. So only when we go to these multi-dimensions that you have these performance issues. And you can see in this loop here, the innermost loop, J, is the fastest, so it's getting elements one after the other. So we're accessing both A and B here in a consecutive manner, which means that we're using those cache lines that have been loaded in efficiently. A and B. Now, if we iterate through this I loop as an innermost loop, then what happens is actually we load up the first element of A and the first element of B, and then the next time round this loop, we actually, jump m elements. So we jump to the next thing of the first dimension of A, and that'll be m times m elements away. And so that probably means as long as m and n are bigger than a cache line, bigger than 16 elements, say, we're loading up a brand new cache line to do that, and loading up a brand new cache line every time. And that means that we're going to have a pattern where we have to do a memory load for every operation, every single addition we're doing here. Whereas over here, we're only doing reload for every 16 additions we're doing over here, depending on the size of A and B and the actual hardware you're running on. And exactly the same in Fortran, except in Fortran, it's this first dimension, the leading dimension, which is in contiguous. So here, if you jump over J as the innermost loop, then you're going n elements each time. So there's a new cache line load each time. But just swapping these loops over gives you much better performance because the innermost loop is where you're doing your memory. So if you're looking at pretty typical computational simulation applications, and you've got multi-dimensional arrays, then this is the most important thing to get right, making sure that any loops you do over them, where possible, you can loop in the format where you're going through the innermost dimension first, like this in Fortran or like this in C. Now, of course, there are some applications, some algorithms where you need to skip over the memory structure and you're not looking to do contiguous elements. And then there is, other things you may need to do to optimize your memory access and rearrange your data structures. And there are some algorithms where you have to do both patterns as well. And there are things we can do, as we'll see, to optimize that as well. But in general, making sure you have the best contiguous data usage of multidimensional arrays is a thing to do. So yes, dynamic size arrays are also often very useful. So in C, these would be arrays where you malloc and free them, or in C++, these would be new and delete, or these kind of arrays. Although I know the newer C++ is it has slightly different memory management things, and quite often the memory management is automatic, so you're not doing new and free. But anything you define at runtime, anything where the size is defined at runtime is a dynamic array. So the nice thing about dynamic size arrays in Fortran is you can pass. Fortran does allow you to do this thing where you don't have to define the size of arrays at compile time for when you're passing data into routines. So you can pass in assume size or assume shape arrays, and the compiler will generate the code to deal with that at runtime. and that's perfectly legal, and it's very similar to passing in a pointer in C to a Fortran into a routine, so that's perfectly allowed. Some address calculation is still need to do this. The compiler will generate some address calculation for this, but it's quite good at doing that, so you don't need to worry about doing that. If you're wanting to do, it is also possible in something like C and C++ to do a combination of compile time decided arrays and runtime decided arrays. So here's an example where there's a small fixed size matrix. You could think of this as a tensor data structure, but we want lots of them. We don't know how many we want to decide that at runtime, so we use this malloc statement to create an array of them. But the actual inner data products themselves, where the compiler is going to do most of the work optimizing it, are known at compile time. And so this inner loop, where we're going over the most important bit of the work, this is all predefined, and that can let the compiler do optimizations there. So this can be a way around some of the allowing the compiler to know some of the information about the data structure you're using and not having to define everything as dynamic at runtime. And you can do this again with multi-dimensional arrays with pointers of things. So again, you can, in this instance, there is actually what we're doing here is defining an array which is a single dimensional array to hold most of our data in, and then create two sets of arrays of pointers to pointers to do this, and the outside. So actually we've got two-dimensional, a 2x2 set of arrays to hold our data in here, and then the innermost array is however big we want it. And this is also where we can do multi-dimensional arrays in C. So we have this array of pointers, and this can be as many as we want actually. I think Fortran is limited to 7-dimensional arrays, but I think in C we can chain these together and make as big arrays as we want. Yes, so if we're doing this multi-dimensional array in C, then we can still use this square brackets to index through our different dimensions. But of course, this is actually really doing some pointer arithmetic underneath. So it's doing a pointer load and a pointer store and a pointer lookup for various things. This is generally fine, but it does mean there is more memory accesses per operation that we do here to get to this point. Now, as long as we're doing lots of work in the contiguous dimension here, where it's only the k that's changing for a given loop, actually the compiler can optimize this out and remove the P1 and the P2 lookup for all the operations inside the loop, and uses that common sub-expression evaluation stuff to reduce the cost of these. But if you're jumping around in the loop quite a lot, and I and j were changing as well as having that not being continuous in memory, we're also having to do some more pointer work as well to get around. You can also do other data structures other than arrays, so we can have sort of what we call records or structures. So in C, this would be a struct, or in Fortran, this would be a user-defined type. Fortran 90 user-defined type. And these are good for putting data together, an integer and a floating point number together, or three integers together to represent a coordinate in space, or integers together to represent velocity, 3 components of velocity, or these kind of things. So these can be really nice programming techniques to make your program easy to understand, which is nice, but there are some performance issues with using structures and things like that in terms of how that can then be mapped onto optimized functionality by the compiler. Because you're telling the compiler, these are the data types I want, but the compiler knows that some of these data types may not map easily onto, say, a vectorization operation or something like that. So the C compiler usually preserves the order of the members you put in a struct, but pads data between them to align on on cache line boundaries or something like that. Now, when you're designing your data structures, there are choices you can make here, whether you want to use structures or arrays or something like that. So here's an example, 2 examples in C of doing this. We can create a particle structure where we have the X, Y, Z coordinates, its index and its mass, all in a single data structure. And then we have an array of those, and we have an array of particles. And each one of those elements has, 4 doubles and an integer inside it. And that's what we would call an array of structures. Or you can create a structure of arrays where we can create a structure which is the particles, all the particles together, and then each one of those we have an array in. So at the first element of X, and the first element of Y, and the first element of Z, and the first element of index, and the first element of mass represent the data for a single particle. And then if you move on, you get a different, the next particle and the next particle. This one here on the left here, array of structures, is a nicer sort of, at least from my point of view, encapsulation method to make the structure understandable in your program, but it doesn't map well onto things like vectorization. So say if you're doing an operation where you want to sum up all the X components or sum up all the masses, you have to iterate through each particle, take out the mass from that particle and then do some work on it. Whereas over here, you already have all the particles of masses in a single array, and you can manipulate them yourself. So it depends on exactly what operations you're doing on the particles themselves as to which one of these gives you best performance. But it can often be that the structure of arrays is a sensible way to go. So the array of structures, the first one, this is the array of structures, has good temporal locality. So, okay, if you want to do lots of operations to a single particle and then move on to the next particle, that's a good thing to do. But it has poor spatial locality, i.e., if you want to go across particles, you have to jump around in memory, because each part, if you want to only do something with a mass on each particle, you're also loading in the X and the Y and the Z and the index, which you may not need. And it's not great for vectorization. And the alternative, the structure of arrays, has better spatial locality. So you can use all the data for the X points and all the data for Y points together and all the data for Z points together. But if, for instance, you needed to do something across a single particle, then you're going to end up having to load 5 cache lines in to get all the data for that particle rather than a single cache line as you had before. The structure of arrays, so you are you're getting slightly ahead of me, Reese. We will get there, but there is definitely an advantage of mixing the two. No, it's okay. You don't have to apologize. It's nice to see. So the structure of arrays can definitely be better for vectorization if you're working on individual components, but it's less natural. You can also do what people called array of structures of arrays. So there's a shorthand for this. Array of structures is called AOS. Structure of arrays is called SOA. And then this is called AOSOA, array of structures of arrays. And then you can have, for instance, structures of arrays of structures. And so here we've got a structure which has arrays in it. And then you can have another array of those structures. And that can be sort of the least worst of both worlds, in that if you've got to work with small numbers of particles together, you're likely to have them all in a similar place. And if you have to work across an individual component here, you're also still likely to have most of the things that map to vectorization in a single place. And indeed, you could actually design your data structures, as Reese has said here, in other ways where you have X, Y, Z as an array of structures, but mass and index as a structure of arrays. So it all really depends on exactly how you're going to use your data in your program. And of course, this will be varied and that will impact your design. So structure of arrays versus array of structures versus array of structures arrays, it can be a nice way of organizing your data so that you give the compiler the best chance to optimize it when it's going through the program. The reason we bring it up you know, it's a little bit of a nasty underlying thing to have to think about, but at least it's one of those features where you can think about it when you're starting to look at your program and design your data structures. And so it's not just, okay, I want to put everything into arrays because arrays are good for memory and for cache loads. It's thinking, how will I actually use this data when it's being used in the program, and what does that imply for how I design my data structures? If I'm going to always be doing things on separate components like X separately and then Y separately and Z separately, then structure of arrays is a nice way to go. If I'm always going to be doing X, Y, Z on a particle, then array of structures is a nice way of going. And if I'm going to be doing something in between, as Rita said, or is highlighted here, then I may need to have different structures where I only keep the X, Y, Z for the particle, and then I put the index in a mass somewhere else. And so it's worth considering these features when you're looking at your program or looking at redesigning your program for optimization. Objects are similar to structures, but more opaque, because you don't, in a C or Java, C++ or Java program or something like that, you're not generally yourself designing the object. The language is doing that for you. One of the main features of objects, of course, is that generally they're all about restricting visibility of data from outside the object, and then providing accessor and setter methods to get data in and out. This access functionality, as we discussed yesterday, can be a bit of an overhead, because it adds function calls in and memory copies for moving data around to get in and out of data objects. So if you're designing object-oriented program, you wouldn't necessarily want to have a individual function call to access every part of particle here and get you the X component of a Y component of a Z component. You might want to get a function call to access an individual particle and then return all the data associated with that particle. Because if you have to have a function call for each one of these elements, that's going to be 5 times the number of function calls than if you return the particle as a whole. And so those kind of features are worth thinking about when designing the program. Now, of course, there are ways around some of the overheads of function calls, inlining functions and things like that. But in general, thinking about those kind of that granularity of your access to data objects, and particularly for data objects which are in your core computational kernels, is important to make sure that you get reasonably good performance of an application. Trees and lists are great programming objects for certain algorithms. They sort of map naturally to certain things that you need to do, and sorting lists and maintaining and growing and shrinking data structures and these kinds of things. So from a programming point of view, they're really nice structures, but they have the same problem as sort of pointer arrays, but actually you have sort of these extra overheads to get the data in and out of them. You have to find where they are in the list and traverse some sets of pointers to get there, and that costs you something. And they're generally also quite hard for the compiler to sort of understand your access pattern, which means you could easily be jumping around in memory and not getting this nice spatial locality which we're looking for reuse in caches. So what we want to do is, of course, try and get better performance for these kind of things. So really, for sort of computational simulation applications, we look to avoid things like linked lists and those kind of things, and replace them with arrays, even though that might make the functionality we have on the program harder to implement. So even though that might mean making a much bigger array so we've got space to put data into it when we get new data, the nice programming feature of a linked list where you can easily just add stuff to the end of it also tends to make it hard to optimize memory accesses and those kind of things. So those things are also worth bearing in mind. Now, of course, that's not necessarily true of all programming languages and all approaches. C++ and programming languages like that have quite nice features for vectors, where you can do some nice vector growing and resizing things. Now, they're still going to be expensive, but the underlying, if you have to grow the vector, if you have to add things to the end, if you have to append data to it, they're still going to be expensive operations. But those inbuilt data structures tend to be quite highly optimized so that the actual computations with them tend to be efficient, even if growing them and moving stuff around them won't be. So there are trade-offs. So you can still use some of these functionalities like the standard template stuff in C++ or vectors or these kind of things. But it's just worth bearing in mind that there are overheads associated with some of the functionality of the nicer data structures to use because they're nice to use. They have sort of wrapping code and they have features which don't easily map onto contiguous memory or nice temporal or spatial locality or accessing data with low overheads. Now, caches, and Mark may have spoken a little bit about this morning in OpenMP. Caches, like we talked about yesterday, have certain features associated with them, generally to do with how they're implemented. And to get a cache to work efficiently in hardware, you need some policies for how you map data in memory onto data in the cache, onto a place in the cache. Theoretically, what you'd like is the cache to be just like one big heap. And when you need to put a new thing in, you find the oldest thing that's never been, not been used for a long time and get rid of that thing and put the new cache line in that place. But in reality, this would be quite an expensive thing to do in hardware every time you, either in keeping track of data accesses or searching large caches. And the AMD L3 cache on these processors is 256 megabytes in size. So if every time you loaded a data structure, a data cache line, and you had to search 256 megabytes on the processor, you'd have a pretty significant overhead. So instead, they go for these block-based direct mapped cache with 8-way or 16-way associative stuff, which means that there's an automatic way, there's a quick way to calculate where a cache line will go, and then that gets mapped to a block, and then inside that block, then you have some quick feature to work out which particular line to replace. And because there's only 8 or 16 lines or something like that in the block, it's easy to keep track of which has been used soonest. The challenge to that, of course, is that you can get scenarios where multiple data structures you're using map to the same cache block. And even if theoretically you should be able to keep your data in cache and reuse it nicely, the fact that you have multiple data blocks, multiple data structures map into the same cache block means you can run into what we call cache thrashing, where actually each time you load up a new thing, it throws out one of the old things that you were currently using in the same bit of code, because they're all mapped into the same block instead of two different blocks in the cache. Now, there are ways around this, and particularly if this is happening, you can pad your data structures so you make them slightly bigger. This tends to only really happen significantly when you have data structures that divide sensibly by 2 or by a power of 2, so they're likely to map to similar places in the cache. So you can pad your data structures to make them slightly bigger than before, and then that will offset them from other data structures. And then, of course, once we have that data in cache, we want to make sure we loop over the data sensibly. So that's what we've already talked about in the spatial locality in the loop structures. Once we've got our data in cache, we want to make sure that we use all that data we've loaded in that cache line rather than wasting that memory bandwidth that we've just used. So looping fastest over the corresponding elements, or if we're in a structure, using all the bits in that structure that we've loaded up, not just the one element of it. And it can make, significant performance improvements for your code. So here we've got an example of Cray output, actually not on this ARCHER2 system, but from Archer, of an operation where we had bad cache alignment between the data that was loaded up, and it triggered quite a lot of cache misses. So we had quite a low number of operations per cache miss, and so we are here then loading much more data up than we want for every cache miss. So if you think that a cache line maybe stores 8 or 16 elements, and say 16 elements, but here we're loading a cache line every 9 operations that we do, we can see we're not using that in that D1 cache, not level 1 cache, but D meaning data here, but level 1 data cache. We can see we're not efficiently using the data we've loaded into that cache. Whereas if we optimize the code to get good usage, we can see now we're up to 20.51 operations per cache miss. So we're using all that data in the cache line and using it multiple times to be able to say we're using that. We're getting much better reuse there. And you can see here from Cray, our D1 cache hit ratio has gone up to 95.1% for this particular bit of code, compared to here we had a D1 cache hit ratio of 89%. And the difference between 95.1 and 89% is not huge. It's only 6% difference, but it translates into a 100% difference in the number of operations we get through per cache miss. And so these are the kind of levels we need to look at: 95, 97, 98% cache hit ratios on the L1 cache to give us good performance here. And you can see, even down here, that was spilling out into L2 cache misses as well. So we've still got quite high hit ratios here, but here there was 600 operations, nearly 700 operations per L2 cache miss. But here we've doubled that to sort of 1400, and actually we get a pretty much 100% cache hit ratio on the L2 cache now that the code was changed to improve the cache alignment. Now there are times where just making sure that we go through the memory in the correct way is not going to give us the best performance we can for a given piece of code. And that can be because you maybe have multiple arrays being loaded up in the same loop, and they're loaded up in different orders. So one will be indexing over a different array dimension than the other. So there is a way of programming called cache blocking. It's also known as loop interchange or strip mining or loop tiling or loop blocking. What we do here is we design our algorithm, our implementation of our algorithm, to reuse data that we've previously used recently, and to reuse data we've loaded in cache lines sensibly. So what cache blocking you want to do and how big the blocks are really depends on what kind of hardware you're running on. So things like your L1 cache size, cache lines, but in reality it's also something you can just do by trial and error. So you can sort of auto-tune the code, run it with different parameters, and see where you get your best performance. Now here's an example. It's not a sensible example, but here's an example of loop tiling. And so here in our operation, what happens is we're going through this is in C. We're going to go through this in a certain order. Now you can see the challenge with this array structure here and this loop here is what we're doing effectively is a transpose between A and B. So we're going through A in the correct order from a contiguous memory point of view, because we're loading up innermost loop is J, the fastest and most contiguous data is on A is J, so we're going through in that order, and that will be optimal for A. But it's exactly suboptimal for B, because we're iterating through this in an alternative way. We're using the other, we're flip the indices here because we're doing this transpose, and there's no way around. I can't reorder these loops here, because if I change these loops around, B will be better, but A will be worse. So it's just a feature of the algorithm. This is what we have to do. And so if we keep it like this, A will get the best cache use, perfect cache, the best cache use we can get, and B will get the worst cache use we can get, and there's nothing we can do about it. But what we can actually do instead, of course, is we can chunk it into small sections like these, and instead of going through the whole array, we can go through individual cache lines potentially, and iterate over those, and that will potentially allow us to do a good access pattern here for A still, because we're still iterating over there, but for B, because we're not going over large iterations of J, we can still keep some of that data locally in memory. So we can still say, actually, instead of loading up this whole, going through this whole array section, whole array row, but once we're going to go for a chunk of that row and then move on to the next chunk, and then to the next chunk, and on to the next chunk. And so that means for B in this example here, yes, each time we go around this inner loop, we probably go onto a new cache line. But let's say we set B equals to before here, we load up 4 cache lines. So that's 4 cache misses for this first set of inner loops. But then when we go around this outer loop here, this I loop, we'll go back round to the next element of those cache lines. So they should still be in cache. And so we take 4 cache misses for B on the first iteration. But on the second iteration of this loop, we take no cache misses for B. And on the third iteration of this loop, we take no cache misses for B. And the fourth iteration of this loop, we take no cache misses for B. So overall, accessing B now has the same number of cache misses as accessing A, because A takes a cache miss at the beginning of this loop, and then it'll take another cache miss when it iterates this outer loop, and then another one, and B has got exactly the same. And if we can tune this so these sizes are correct, the size in J and the size in I are correct for the cache we're working with, and so that will be how associated it is, how many elements in the block we can map our data into before it gets kicked out of a cache, and our cache lines sizes, 64 bytes or something. If we can tune these two things sensibly, then we can get back to sort of perfect cache, or as good as possible cache use by doing this kind of blocking. So whilst the reality is that for memory accesses, what we want to do is this kind of thing here. This is perfect, and if your algorithm maps to that everywhere, then that's what you should be doing. Of course, the reality is that a lot of algorithms, a lot of implementations, you have nasty features in them, like not all the arrays in the same loops are going over the same indexes at the same time. So you may have to optimize those by doing some of these optimizations. And we can see a similar thing for loop tiling over vectorization. So we'll talk about vectorization in a little bit, but this loop here is going over the array elements in the correct order, so that's good. We're going over J in the correct order. But here, this J minus 1 and J plus 1 will mean that the compiler can't vectorize this loop, because vectorizing it would mean doing J and J plus 1 and J plus 2 and J plus 3 all at the same time. And because I rely on J minus 1 and J plus 1, those values won't have been calculated properly for me. So I can't vectorize it. But here what we've done is actually, okay, let's change the loop ordering. Let's do the loop ordering of the incorrect structure. So we've swapped our loop ordering around, but then we've moved our J loop to a higher level to enable this to be vectorized. So we're actually iterating over the i's now. So here what I've done is not only change the loop ordering, but actually change my data structure setup. And now what we can say is we'll go over the j's, and then we'll go over we'll go over the i's and the innermost loop, and then we can vectorize this. And so this is a different kind of loop blocking, but still also potentially a useful one for getting around sort of vector dependencies and those kind of things. Good question. So are compilers able to take care of loop tiling by themselves, and is it built into for example, transpose functions in MKL and similar libraries? Yes. So for question 2, loop tiling and loop blocking and these kind of cache blocking will definitely be implemented where it's beneficial in things like MKL and other maths libraries. They definitely will have gone to that level. Some compilers can do loop tiling by themselves if you've got a simple loop where literally these are the structures you have. Then there are some compilers which will consider optimizations like that. In reality, of course, most applications have much more complicated loops where there's many more lines in here than A equals B, and then it becomes much harder for the compiler to spot those kind of things. So the reality is that for most proper applications, where you're not just a kernel maths library, you probably have to do this kind of loop tiling yourself if that's something that's needed for your application. Finally, another cache optimization you can do is also consider reuse of data. So here we've got 2 loops in our code. The first loop goes through here and says A equals B times 2. So we go through the whole A array and we say A equals B times 2. And then what we do is we come and do some other work and we say A equals A plus 1. Right now, and I appreciate these are pretty simple, right? Because we could just say here A equals B times 2 plus 1 and get rid of this final loop here. But we're really just illustrating a point here. If it could be that this is more complex functionality going on down here, and so this is perfectly acceptable. This is fine. But one of the nasty things about it, if A and B are big enough, of course, is that here you iterate through the whole of the A array. You've loaded it all up from memory into cache. But by the time you've got to the end of the A array, actually all the stuff you loaded at the beginning, the first part of the A array, has been kicked out of cache by B or by new elements of A. So it's no longer there anymore. And then you come back around to this here, and what you end up having to reload A back into cache from memory. And that's, if A is big enough, that's certainly definitely possible. Whereas what we can do is fuse these loops together and do the A equals B and the A equals A plus 1 in the same place. So once we've loaded A in here, then we're reusing that in cache and we don't have to do that second data load. And so that can address this problem. But if multiple loop nests process a large array, the first element out of an array will be out of cache when the second loop starts. So we can completely fuse these, or we can do a partial fusion where one loop contains other loops. And so this is an example of a partial fusion over here where we're not actually completely fusing both these inner loops together. We're doing them separately, and it could well be that you want to do that because these are slightly different loops. But you're still reusing some of the A that's been loaded in because you're not iterating over that J outer element until you've done all your work on the inner element. So this can be quite a useful functionality. Of course, it will potentially rub up against some of the things we talked about yesterday, which actually, if you make your loops too big and put too much stuff in a loops, you can run into things like register pressure, which can reduce your performance. So there's a little bit of a balancing act here in between cache reuse and then making things too complicated for compilers to get good performance out of it. But in general, this is a good approach to look for if you've got lots of cache misses, but you're accessing your data in the correct way in the correct loops. if there are a way to put bits of code together which are using the same data in the same places, then you can improve your data reuse. It's also quite often possible to find applications that are written in such a way where you call a function that iterates through a data structure and does some work on it. You return from that function. You call another function which uses the same data structure, goes all the way through that function, etc., etc. And again, you're seeing the same problem there, this idea that you're iterating through a data structure and then all the way to the end and call another one. So it can be quite nice sometimes to hoist the loops out of those routines and call them from an externally, and then pass in indexes values instead. So something like this here. If we can assume that subroutine A and subroutine B do something with A and B, sub1 and sub1 and sub2 here are functions, and here we see sub1. It goes all the way through A and initializes it, and then we can say sub2 is equivalent to this function down here. Well, calling these functions, putting these in separate functions is fine, and calling them as separate functions is fine. But we're going to have that problem again where we load up all the, we create all the A array in cache, and then we have to come back down and recreate it. Now, we don't really necessarily have to get rid of those functions because they're nice from a programming point of view. But what we can do is restructure them. So actually, maybe we pull out this outer moat loop outside both of the functions, and then call these functions over that loop. And then we may get that data reuse we want. Now, of course, there's other things going on here we want to care about. This function call overheads here, and if this function really is this small, it's probably not worth having as a function. But that's just an example to make it easy to see on the slides. Generally, these functions would be more complicated than that. And that can also be useful for things like OpenMP or OpenACC or these kind of directive-based parallelization approaches where actually, here you do OpenMP inside one routine here to parallelize it, and then you do OpenMP inside the other routine, but you've got a overhead of starting the OpenMP in both these places, whereas actually we could do an OpenMP loop at this higher level here and call the subroutines inside that. And that can be a beneficial way of doing things. Fortran array syntax is generally quite a nice language feature to use, and generally allows the compiler to do nice optimizations and vectorizations of these calls. The only nasty thing about it is it won't let the compiler do these kind of fusion operations, so it won't produce those kind of things. So again, here you'd want to structure this array syntax so you had A equals B times 2 plus 1 in a single line, and then that would enable you to do that kind of optimization instead. We briefly discussed yesterday that there is this sort of functionality on the processors to do virtual memory and then translate it into real memory. So what we call using the TLB, the translation look-aside buffer, which itself is a sort of cache on the processor. And if you've got lots of sort of small memory operations, you've got lots of data accesses, the TLB accesses of a TLB cache can become a source of an overhead. The nice thing is that there is an easy way around of fixing this. So the TLB is used when you load a new memory page. And memory pages are generally of a certain size, 4 kilobytes. But you can also use larger pages. So you can specify, actually, I want to use pages which are bigger, all the way actually on the Cray up to 2 gigabytes. And that can give you reduce this overhead of looking at these translations. And we've got a nice way of doing this on the Cray, which is this module load Cray PE huge pages. You recompile your code, and then you can use them at runtime. And that can give you some performance benefits for applications, particularly if applications do lots of malloc and free and dynamic memory operations, and that can be a useful benefit. And actually, the Cray is quite nice because it lets you compile with huge pages. It doesn't matter what size you use when you compile with them. and then you can change them at runtime and try out different huge pages without having to recompile your code. Prefetch is available is a feature of most modern processors, and so this is the idea that it tries to load in new cache lines before you've actually asked for them based on memory access patterns that you're using. So if you're going through that array in a nice contiguous manner, it will try and load the next next cache line before you've actually requested it, so it's already there. Generally, you need to be accessing memory in a nice, simple line, in a nice contiguous way for the prefetcher to do a good job. But if your loop has quite a lot of data that you're processing over, quite a lot of separate data that you're using inside a single loop, then the prefetcher is going to run out of options for deciding what to prefetch and may not work as well. So that might be one of the reasons, as well as register pressure, but one of the reasons where you may want to split loops apart, some big loops where you're doing lots of work, but potentially on sort of separate data structures. You might want to do that separately, because that will let the hardware optimization of things like prefetching and the caches better cope with the work that you're doing. But prefetch, you can also do this manually. So there are, I don't think we have examples in here, but there are manual programming techniques you can use to specify a prefetch, and they vary from compiler to compiler and system to system. But you can quite often put a pre-processing directive or macro into your code to say, at this point, prefetch some data. And so if you know you've got a slightly different memory access pattern, but it's regular, you may be able to quite nicely write some prefetch routines to do that for you and insert them in the correct place in the code and actually reduce some of your cache overheads, cache misses, by doing prefetch manually. So that's worth looking at. Finally, I think pointers in C, C++, and to some extent Fortran are very useful, but can seriously inhibit code performance optimization by the compiler. And that's because the compiler finds it very hard to do optimization reasoning on pointers, because a lot of the reason it's trying to do in its optimization is to work out if data values are independent, and pointers can point to anywhere in memory. So you could have multiple pointers pointing to the same element of an array, and that would negate some of the optimizations a compiler can do. So to be safe, the compiler will reload all values after a write for a pointer and synchronize all variables with memory before reading through a pointer. And so that means that either the compiler won't do optimizations, or it will add in extra functionality in your code that you don't really need extra instructions, because it thinks the pointers might be doing bad things. In general, Fortran doesn't have pointers, but there are some places where you can do pointers in Fortran, Fortran is a little bit better at optimizing around pointers, because pointers are a bit more restrictive than what's in C, and so you can only point at particular variables which are known as targets, and that means that you can have the compiler has more chance of optimizing everything else. But in C, they really are unrestricted, so lots of use of pointers can seriously inhibit performance. What you can do to get around this is add in some functionality which helps with this. So there's a C99 keyword called restrict for the C programming language, which tells the compiler that you're guaranteeing that pointers always point to separate data structures and they're never aliased and never pointing to the same place. And then the compiler can do more rigorous optimization and reduce some of the safety stuff that it does, as long as you've guaranteed that, right? So of course, this is up to you. You're guaranteeing it. So if you get that wrong, your code may be incorrect, but you can do that. So you can put a restrict keyword next to everywhere you use pointers in the language. You can also generally pass something to the compiler as a flag. So for the Cray compilers, this might on C, this might be H restrict, or for GNU, -F strict aliasing, -F argument no alias, -F argument no alias globals. Global, if you pass all those in, that will turn on assuming restrict everywhere. Now, the AMD compiler is not quite as up to speed with this kind of stuff yet, so it doesn't really have the proper argument aliasing stuff here. So that may not do the same optimizations, but that will come over time, I've no doubt. But these, if you're doing C or C++ programming, these are very useful things to consider to see if they provide optimization for your application, because you can just do them at compile time and you don't actually have to change your code. And as we'll come on to see, the aliasing stuff is quite important for vectorization. So for memory, really, what we really care about is memory ordering, particularly for multi-dimensional arrays, and this configurations of your data structures. So this stuff here, memory ordering, spatial locality, and data structure design and inclusion in your application. Then there can also be sensible things you can do to reduce issues for things like loop tiling or cache blocking, loop fusion, and loop loop hauling, and possibly loop splitting as well, depending on the problems you have. But those can all be useful things to do to improve reuse of your data in a cache, which is all we're trying to do here, and reduce the number of cache misses you use, and therefore increase the number of arithmetic operations you can do per load store operation, which is what will get you good performance for most applications. Is there any questions on the memory stuff? Right, if not, what I will do is start on the next bit, which is the vectorization stuff, but I'm going to give it a 5-minute break. And so we'll start in 5 minutes time, and then we'll whip through the vectorization stuff. And then you can come on to practicals. But any questions in the meantime, drop me a message. And what I'll do is I'll make sure I've updated the slides that we're using on the website just now as well, because I'm not sure you've got the latest versions of these slides. In 1 second, I'll do that. But 5 minutes and we'll kick off the next one. And we've talked quite a lot of, when I say we, I've talked quite a lot over the past 2 days. But here's the last lecture we're going to go through, and it's on vectorization. So it's one we've talked tangentially a lot about, but it's worth mentioning for performance on modern processors. So modern CPUs, so the AMD ones, all the Intel ones, the ARM ones that are coming out and are now available, all quite heavily rely on vectorization for their peak or their good floating point performance. And vectorization here means that individual processors, individual cores, can do multiple operations per cycle using what we call SIMD instructions, single instruction, multiple data. Now, these aren't new things. They've been around for a long time. In fact, if you're doing any computing in the late 90s, you'll remember Intel bringing out their sort of MMX instruction set, which was sort of multimedia extensions, and that date was sort of some of the first early vectorization things. But they are very common nowadays for large-scale server processors. And what we're looking at doing is, what they're doing is generally 4 or more floating point, double precision floating point operations at once. And actually, the Intel processors, the latest Intel processors, have 512-bit vector units, which will do 8 double precision floating point numbers at once. And the idea is, if your code is amenable to it, you can really get much higher throughput of your floating point stuff through the processor by using these vector instructions. As we'll come on to see, what can be vectorized is very dependent on what your code is like. But generally what we're looking at here is primarily loops that can be vectorized, and generally only the innermost loop of a loop nest is what the compiler will look to vectorize. But anyway, here's a little bit more detail. Same operation on multiple bits of data. Here we've got a C loop, here we've got a Fortran loop, but we're doing the same thing. We go from the beginning of array to the end of array. We load 2 bits of data, we add them together, and we store them into a third array. And we just do that multiple times until we've got to the end of the array iterator. And exactly the same in Fortran. Load C, load B, store, add them together, store to A. And if we did this normally without vectorization, we'd do B plus C equals A of element 0, and then element 1, and then element 2, and then element 3. Vectorization just does the same thing, but actually instead of doing element 0, then element 1, and then element 2, and then element 3, you do element 0, 1, 2, and 3 together in a single instruction. And that means you can do, in this case, 4 things at once. And the AMD processor we're using are going to be a 256-bit vector units, but there are multiple of them on a single processor, so we can actually do sort of 8 things at once if we're amenable to it. You can actually also do slightly smaller things, so if you're not doing double precision but you're doing single precision, you can do 8 of them instead of 4 of them at once. The AMD Rome processor supports the AVX2, which is also known as the AVX256 instruction set. So there are various different units on there. And so you can see that this can be really beneficial. We can get much more floating point operations done per clock cycle. Now, the reason that it's on there is actually it's pretty easy to implement in the silicon. In the actual floating point units are made out of transistors. You don't need that much extra hardware to do 4 things at once, as long as you're doing the same instruction as you do to do one thing. Because a lot of the complexity is in around just the instruction decode and the setting up the units and choosing what to do. To make it do 4 things at once rather than 1 thing at once, you just have to make the units wider and do a little bit extra in sort of accumulate and carry parts of the operation. And you also have to make the registers wider, so we have to load data in bigger chunks. So we have to have our registers as vector registers rather than serial registers. But because we're already using this idea of cache lines and loading up data in cache lines, we can see that we're already loading up data in chunks. Even chunks are even bigger than our vector units here. So we can leverage that to load data into these vector units more efficiently as well. So it sort of fits within that whole pipeline as well. Now, compilers will produce vector optimizations for you. So they'll take your code and turn them into vector instructions where they can. But it relies on the code being in a form that the compiler can convert to be vectorizable or recognize in the vector variable, recognize that it's vectorizable, amenable to its vectorization. And there are some ways that we can structure our code to make these kind of things more understandable to the compiler. So the compiler, as I said, is only going to be looking to do loops for vectorization. And usually it's only going to vectorize 1 loop in the loop nest. And so by default, it's going to consider the inner loop, the innermost loop. The compiler we'll look, so innermost loop. Now there are different ways for us to check if a compiler is vectorizing well. One is we can look at the compiler output. The other one is we can look at assembler code and look for vector instructions. And the third one is we can turn the vectorization off in the compiler and see if that makes any difference to our performance. In terms of what the compiler can do for vectorization, as I say, we're only looking at loops really. Loops must have a determinable at runtime trip count, so it can't be a while loop or a do while loop. We need to know the start and the begin and the end of a loop at runtime. It doesn't have to be known at compile time, but at runtime. In general, the loops shouldn't contain function or subroutine calls, so you can call maths library functions like square root and things like that. You can call a subset of functions if you structure them the correct way, and there are ways to doing that, but in general, you don't want the loops calling functions, otherwise that makes it hard for compiler to vectorize. And in general, the loop mustn't contain branches or jumps, so you don't want if statements inside your loops. Now again, there are ways the compiler can vectorize if statements with loops with if statements in, but even then you'll generally get reduced performance because it will do what we call sort of loop masking, and not all the vector units will be used. And finally, the loop needs to be big enough to be worth vectorizing. So we know that our functional pipelines take a bit of time to fill up. We know that vector instructions may take multiple iterations to complete, so it may not complete a single vector instruction per clock cycle. But once the pipeline is full, it will. But it may be easily a vector instruction may take 4 or 8 or 6, or a few instructions to complete. So you want the loops to be big enough. And because we're doing, say, 4 or 8 instructions at once, you got to see the loops need to be sort of 64, 128, 256 iterations long before it's worth doing that overhead of vectorization. So we're talking about reasonable sized loops, or with a large amount of work in them, where we don't have any of these things like functions or subroutines or branches inside them. Loops must also have no dependencies between iterations. So a guarded assignment here is effectively I'm only going to update B if this condition is true. And so the reason that the assignment here is B equals C times A, and the guard here is this if statement. If A is not equal to 0, then I can do this statement here. The reason why this is nicer for the compiler to vectorize is actually it can do some of this work before it has to decide. Well, it already knows what the value of this is when it's coming into this loop. So this if statement is easy for it to calculate the result from, and then it's easy for it to do these operations prior to evaluating this if statement, and then only put the store in a guard here. So it can take some of this work outside here, vectorize that, and then do some kind of masking where it says true or false, and assigns the copies of this to be true or false, because it lets it do all those things at once. It can do 4 of these at once. And so that sort of guarded assignment can easily map well to a vector. It can map to vector instructions more easily than a more general if statement where you're sort of not looking at individual data values of individual elements in the array and doing work on those corresponding elements. Does that help you answer your question? The loops must have no dependencies between iterations, because we've got to remember what will happen in this loop here is instead of doing A0 equals B0 plus C0 and then A1 equals B1 plus C1, what we want to do is effectively unroll this loop and do A of 0 equals B of 0 plus C of 0, A of 1, B of 1, C of 1, A of 2, B of 2, C of 2, and do all of them at once. Now, if A of 1 is dependent on a of 0, then I can't do all those things at once because it won't do the right thing. So loops shouldn't have dependencies in them. Either a of I equals a of I minus 1 is a dependency, or a sort of a reduction variable like this, sum plus equals a of I, because the value of sum depends on a previous iteration of a loop. So we may have to get around that. And induction variables are also quite often identified as dependencies in the loop by the compiler. So induction variable here is a variable that gets changed every time we go around the loop. Now, there are ways we can get around using these in our loop, but these may stop the compiler auto-vectorizing our loops by default. And then the pointer alias thing, which we talked about in the memory lecture, may also come into play here. So if you're using pointers inside your loop, then the compiler is going to find it hard to vectorize that because it doesn't know, it's not guaranteed that one pointer doesn't point to the same address as another pointer in a different loop iteration. And so you need to tell the compiler that it doesn't, or not use pointers in there. So the compilers can find it hard to vectorize loops with some of these features. They only vectorize loops which are determinable and inner loops, and only will vectorize one loop, and it shouldn't really have branches or function calls in them. Now, to get good performance from our compiler, what we generally need to do is also make sure that our data is aligned. And what does this mean? Well, it means that the data needs to be set up in such a way that it can load individual cache lines in, and those cache lines will store the data we need to use in the vector instruction. And so these are most effectively AVX or AX2 loads and stores probably most effectively work on 32-byte or 64-byte aligned address. So we need to align our data, and then we need to tell the compiler that we've aligned our data, and then generally it'll be okay. And then unit stride through memory is best. Now you can vectorize code that doesn't go unit stride through memory, but you just won't get as good performance because for each cache line you load up, you're not using individual consecutive elements. You're using an element and then skipping to the element, next element beyond that. And so you're not getting the best performance because you're going to have to do more loads of your data for each operation that you're doing. So let me skip ahead. We'll come back to these, but let me skip ahead to examples of these kind of things where the vectorization doesn't work well. So this is an example here where I've got a bit of code. It's a C code. Now you can see I'm using pointers over here, so this is going to cause me problems anyway. And then I've got code in here which I want to vectorize. Data 1 equals data 2 times data 3, and j equals index. And so I want this loop to vectorize, but it's not going to vectorize because I've got these pointers, because the loop iteration bound may not be known at compile time. Because it's a pointer here, loop size is a pointer, and I'm dereferencing a pointer. Actually, the compiler doesn't know whether this loop size changes as we go on here. Actually, data 1 could point to somewhere that loop size is set, and it could be changing the loop as we go on, and that's not allowed. And it may also see that there's a sort of dependency here between j and index, and it doesn't know what's going on here. So I can restructure this loop here to put the restrict keyword in here, where I'm saying these pointers are restricted, so I can guarantee you they're not pointing to different places. I can take the loop iteration counter, so a loop limit, loop size, out of the pointer and make it a fixed variable, and then the compiler will be happy about that. And then I can tell the compiler with a special flag here saying, oh, actually, I guarantee you there's no dependencies between these loops. That index, which produces j, is not the same as data. And then I'm going to be quite happy. The compiler should be quite happy to vectorize it. So we've not really had to significantly change our code here, but we can address some of the issues the compiler sees and make it vectorize the loop correctly. And you know, this thing here, #pragva ivdep, is actually something which is more Intel compiler specific, but there are different ways of doing it for other compilers. So for the Cray C compilers, or for the Cray Fortran compiler, or for the GNU compilers. GNU compilers, you can usually use IVDEP. Cray Fortran compiler and the AMD Fortran compiler, you can use this one here with this flag. And for the C compilers, you can use this hashprag reclang loop vectorize enable, and that will force, well, and let the compiler know that it can vectorize this loop. We can also do things like this. There's a bit of Fortran code where this is not going to vectorize because there's a dependency here between different loop iterations, because this x is dependent on the previous value of x every time we go around the loop. So we say x equals x plus this, and then we use x, but then the next time we go around the loop, we're reusing the x we calculated on the previous time around the loop. And the compiler will say, well, that doesn't vectorize because I can't use that bit of code elsewhere. I can't sort of do all these operations at once. And so when we can restructure that code to say, actually, oh, okay, let's take the x away from being a scalar variable turn it into an array, and then I can initialize x in a certain way, and I can then restructure my loop so that I do reuse that x that I've turned into an array, and now it's not a dependency between loop iterations. It's independent of each of the loop iterations. Okay, so those are kind of things we can do. We're trading off here memory space for vectorization, but as long as we've got enough memory and as long as this loop isn't too big, and again this loop will vectorize quite nicely, then that can give us some good performance there. There are other things we can do as well. So these are the flags we generally have to do to turn vectorization on. So not all compilers will do vectorization all the time. So the Cray and the AMD compilers will get vectorization by default because it's enabled from the O2 optimization flag, and that's generally on by default. You generally have to tell it what hardware you're running on. So for the Cray and the GNU and the AMD compilers, it'd be sort of march equals znv2. That means we're running on the Cray, the AMD Rome processor, and this is automatically added for us on Archer, so we don't need to care about that. You can actually turn the vectorization off by using this -f no vectorize flag, and that can be useful to see to run your code without a vectorization and see if you get a performance difference. And if you don't, then it's likely your code is not vectorizing well. And then what's really useful and important is you can get the compiler to print out stuff when you compile your code to tell you whether it vectorized things or not. So for Cray and the AMD compilers, C compilers, you can use this -rpass mist equals loop vectorize, -rpass analysis equals loop vectorize, and that will print out whether it vectorized loops or not and why. For the Cray Fortran compiler, -hlist equals A will do the same thing. And for the GNU compiler, -fdump treevec all and give it a file name will tell you you can do those kind of things. And actually, there's more kind of things we can look at there. Particularly for the GNU compiler, there's also some other flags that can be useful. Actually, you can find these for other compilers as well, but the GNU compiler has quite a good list of these, where you can look at all the optimizations a compiler is doing for your code, like -f opt info all will produce either some files or a lot of data, a lot of output when you compile, saying all the optimizations it tried to do and all the optimizations it couldn't do. And these are great places to start looking at. Are there more things we could do with the compiler to get our code to go faster? Is there some places where it thinks it could do better, but it can't because it's not sure it's safe? And if you can just restrict this to say, just tell me the optimizations you wanted to do but couldn't, or just tell me the vectorization optimizations you wanted to do but couldn't. So these are great, and some of these options are available for the Cray and the GNU compiler as well, and the hlist A will do a similar kind of thing for the GNU compiler. Yeah, so as we've seen in these examples here, we can also do work to help the compiler recognize when it can vectorize. So some of these things is removing the dependencies like we saw, so turning a scalar into an array, and then using the array and then doing a temporary and then doing a sum at the end of that array, something like that is great. A great way of doing it. Or can you unroll a loop? So the compiler would vectorize, but actually there's not enough work in that loop to vectorize it, so it's decided not to. So maybe you can unroll the loop to give it more work to do, or combine a couple of loops and vectorize those. And if you want to do potentially unrolling an outer loop rather than an inner loop, there's also ways to get the compiler to do that as well. So it could be that your innermost loop is too small or has some dependencies in to do that vectorization, but you can unroll an outer loop and vectorize across the whole loop. Yes, so there's a good question here, Reese. If you're running in a non-uniform cluster, so you've got different processors in the cluster, in order to use vectorization, do you need to compile for each arch, or is there some vectorization work that can work across multiple architectures? So it's an interesting but complicated question, this. It depends on what the architectures are in your cluster and then what compilers you have available to you. In general, to get the best performance for any processor, particularly on vectorization, you want to compile for that specific processor. And so that means you need to create a binary which matches that processor. There are some vectorization subsets that will work across all the Intel processors, for instance. So instead of using AVX 512, it'll use AVX2, or it'll use AVX, or it'll use SSE. So some vectorization will work across a group of processors, but not quite be as sufficient on all processors. So if you had an Intel Skylake processor and an Intel Ivy Bridge processor, you could create a single executable which worked on both, but was less efficient on the Skylake, because if it used the AVX 512 there, it would be better. There are also some compilers like the Intel compiler, which will let you produce multiple architecture binaries in a single executable, where you can say compile for these different architectures and then choose at runtime which you're going to use. But this is quite compiler and machine specific. So it's hard to compile on an Intel processor and then run it on an AMD processor and get vectorization performance that works on both, or even get vectorization that works on both. And then, of course, going between architectures, so x86 to ARM, you really have to just compile a completely different binary because of the different instruction sets. So the answer is yes, possibly, maybe, it depends. If your machines are close enough and your compilers, and you're using the certain compilers, you can sometimes produce a single binary which will work efficiently across them all. If your machines aren't close enough, or you've not got the right compilers, you can often produce a binary which will work across them all but not be optimal in all places. So often it's useful to recompile for a particular architecture you're running on. If you have specific questions on that, Reese, then do drop me an email and we can look at it in more detail. So you can do outer loop unrolling. And then if we look at this alignment in a bit more detail, so vectorization will work with data that's not aligned. And alignment means that the start of your data structure starts on a cache line boundary, so that when you load up a cache line into memory, that can then be mapped directly into a vector register, starting at the beginning and moving on. So say our cache line is 8 elements long and our vector registers are 4 elements long. If I load up my data and my data starts on a cache line, then I can do my first load from here and then my second load from here, and I don't have to do any extra work. If I have data that's not cache line aligned, well, I can do work. But say this is my data here, and my cache line would be, let me get a pen to draw on this. My cache line would be this chunk here. That's the first cache line, and this is the second cache line. And in fact, let me erase all link. I did that slightly wrong because we're assuming our cache line is 8 elements long. So this is my first cache line, and this is my second cache line. If my array doesn't align with the beginning of that, when I load it into memory, then it will be able to do a it will have to do some work, because this part here would map directly into a vector register, but this part here wouldn't, and then this part here wouldn't. And so what happens is the compiler says, I can vectorize this, I will vectorize this, but if your data is not aligned, what I'll do is I'll do multiple data loads for multiple cache lines. And what it'll actually do is it'll create these 3 different bits of code. It'll create a kernel loop, which is fully vectorized and runs vector instructions. But it also creates a peel loop and a remainder loop, which are serial instructions, which do these bits of the work, which are not going to map into the vector registers sensibly. So it'll do this bit serially, it'll do that bit serially, and then it'll vectorize that instruction and that instruction. And then it will end up doing some serial stuff over here to finish off, because unless our data structure exactly divides by the number of vector registers we have. So if we have unaligned data, it can vectorize, but it may not be as efficient as we would like, because it creates these extra things. It creates this peel loop at the beginning, and it has to do more data loads, and it has to do some data shuffling around. If we do a properly aligned, if we have properly aligned data, then it can do a kernel loop and potentially a remainder loop. So it just creates 2 different versions of your loop. And if your array size exactly divides by the number of vector elements you're using, then this remainder loop won't even be executed, and it'll just be the kernel loop that gets executed. So aligned data is best, and that gives us the best performance on the system. The question is, for vectorization, the question is, how do you align data? Well, we can do it using these new functions. So we're talking about dynamic data here, but this is mm_malloc _mm_free functions, which let you do malloc and 3, and you pass in this new parameter to your mallocs to say align it on 64-bit boundaries or 32-bit boundaries, and so that will work in C. You can also do the same thing for static data, so you can use this attribute aligned, and that will automatically do it for you. In Fortran, you can use this bang dir dollars. This is a preprocessing directive. A directive, and it says align this data. And if we're going to do allocatable data in Fortran, so dynamic data, we can do it this way, and then pass in this directive to align it as well. And so this aligns the data properly for us, and then we can use it in our code to make sure that we are getting the best performance out of the compiler, out of the vectorization. Now, the nasty thing, of course, is that once we've aligned the data, we also then have to tell the compiler we've aligned the data. And there's a number of different ways of doing this, but generally the easiest one here is to stick this at the beginning of any loop you want to vectorize. And these are OpenMP SIMD pragmas, but they let you say hash pragma OMP SIMD, the data is aligned. And that tells the compiler you've done the work of aligning the data for it. And that lets you get the best performance. Now, these are compiler independent directives. There are also some compiler dependent directives. This works with this will work with the Intel compiler and the AMD and Cray compilers, as long as you use this flag here, enable vectorize pragmas. And then there are some other things which may work on different compilers as well. So there's multiple ways of doing this, but this is what you have to do. There are also, we may also care about how we pass our data into subroutines for Fortran, because subroutines in Fortran have multiple different ways we can pass our data in. We can tell explicitly how big our data is using these this is explicitly telling the data sizes, and then this subroutine will generate code internally, which is based on contiguous data. But if these arrays aren't actually contiguous, then it will generate the code to pack the data into that contiguously and unpack it on the way out. Fortran also lets us do these assumed size arrays where you don't tell it at compile time how big the array is. And then what the code will do, the compiler will do, is generate two versions of a loop, one where it's assuming the code is aligned, the data is aligned, and one where it's assuming the data isn't aligned, and then check at runtime to do that, to call the correct one. So we still need to make sure those arrays are aligned. Also, it's a good question. Why do you have to use MM3 for Mn Malloc? Actually, I don't know the answer to this, but you do, because if you don't use MM3, it will crash your application when you try to free that object. I think it may. So Malloc and free are actually quite complicated operations in that they interact with the operating system and the virtual memory pages that you're given, and those kind of things. So I think it may interact with a different place in the memory subsystem from a different part of the operating system function calls, and so it doesn't vectorize. It doesn't pick up that the memory you're freeing is in, it doesn't work out. If you use the wrong version of a free, it doesn't know what memory you're trying to free. But I will check and get back to you on that, because I've never actually looked up why you have to use the $_mm_free to free aligned data, but you do. So is it still possible to vectorize something like b equals a with indirect? So this is what we call indirect addressing, where the value you're going to look up is a value is an index stored elsewhere. Yes, it is possible to vectorize it, but it becomes harder to vectorize it because the compiler doesn't necessarily know your data is contiguous when it goes to vectorize it, because it's hard for it to understand that. Now, the interesting thing, Luca, is that b equals a c is actually a very common approach that was used in vector codes for proper vector systems a long time ago. So actually, I'm just about to get to it, but we've got a whole slide on this here as to how to vectorize those kind of things. So it is definitely possible to do indirect addressing vectorization operations. Here we're talking about in Fortran, but it is possible in C. But you have to be a little bit careful about how you structure your code and how you get the compiler to vectorize that. So I'll come on to that in 1 second. So yes, in the assumed size array, and then you can also do something called assumed shape arrays for Fortran, where you don't tell it how many dimensions you have and you don't tell it how big the dimensions you have. And again, the compiler will generate subroutine, generate code, but in this case it assumes that the data is contiguous, but we still need to tell the compiler that it is. Okay, coming back to Luca's question, indirect addressing is something we quite commonly see in old vector codes from vector systems, because that was generally how it was often most performant to implement vectorization in the past. And so this is the idea where we have an index array which we look up and then use to specify the data we're actually using. And the problem is the compilers find it hard to vectorize this because it assumes that this is a dependency between the loop iterations, because it doesn't know what index really is. So it doesn't actually know that you're following some sort of nice contiguous pattern here. And so what this can end up doing is it can vectorize, but it uses what's sort of calls gather and scatter operations to unpack index data, pack and unpack the data. So it sort of gets the data for A, B, and C and packs it together and then vectorizes the operation and then unpacks it. And this may not be as efficient as we would like, because actually if these things are all contiguous in memory, then we're undertaking some operations that we don't need to do here. In Fortran, this can also be a little bit more complicated, because from a array notation perspective, we can actually also end up creating multiple loops and doing gathers and scatters across those loops, because actually if we did here we do gathers and scatters, and this will do some kind of vectorization, although it may be slightly suboptimal. Here, actually what it does is it sums up all the data into a temporary loop, and then it assigns it back at the end, doing into the A value if we do it in array indexes, and that's even less optimal because it's doing gather and scatter on both loops. So in your example for the C code, where you had this B of I equals A of C of I, it's definitely possible to vectorize it, but we need to play a little bit around with the compiler to see if it's happy to vectorize it, depending on the compiler you're using, and then possibly give it some hints as to how to vectorize this to help it to do that. So if you have a specific code in mind or a specific bit of code in mind, I'd happily have a look at that for you and see if there are things we can do to optimize, to get that optimizing well on a system like ARCHER2. The compilers, yes, so the compilers, this is an example of a kind of output we get from the compiler when this is from a Cray compiler, and this is where we passed in that minus H list. I don't know why I'm trying to write this, I could just type it, equals A in as a compiler flag. And it will tell us here, this is the kind of thing it tells us here, look, I've gone through this here, there's a loop starting on line 16, it's not being vectorized because there's a dependency here. It thinks there's a dependency on this X statement here, because this X is sort of there's a recurrence of this X statement here, so it doesn't like that. Or in fact, what it's actually saying here is the Cray compiler is contradicting a little bit what I've already said, which is generally the compiler will only vectorize the innermost loop, this one here. What it's saying here is I've tried to vectorize both loops, but I can't because the outermost loop won't vectorize, because there's this Y of I would be the same for each iteration of the outermost loop, so I can't unroll it there. And for the innermost loop, I can't vectorize it because these X's seem to be linked. There seems to be a dependency between these X's, and I can't do them all at once. And this is the same example we saw before. And if you ran this, this would take, 1.4 microseconds for an iteration of this loop. If we turn this X into an array, we trade memory for better performance. The compiler then says, actually, no, I can vectorize this loop. I'm going to vectorize both these loops. I'm going to vectorize that loop there, and that's what it's saying here. And then it's going to say, I'm going to vectorize this outer loop here, and interchange them and fuse them together. And what it's actually doing is actually, you can see what the compiler is doing here is it's doing some interchanging and some fusing. So what it's saying is I want to, I'm going to now actually combine these two loops. I'm going to take this bit of operation, I'm going to put it in here, and then I'm going to do some work inside here, and I can vectorize this, and then we get a performance increase. So it's not 100% performance increase. This is on small vector units, but it is a performance increase on this bit of code. Now, finally, and I'm nearly finished speaking, you'll be glad to know. Finally, there is some easier ways of doing the vectorization, or forcing the compiler to do vectorization, or forcing some compilers to do vectorization, and that's using some stuff which is an OpenMP4. Now, OpenMP is generally about threaded parallelism, but it also, the newer versions of the standard include some directives to do vectorization called SIMD directives, and these are things that you put onto your loop to say, I'm telling you that this loop can be vectorized, please vectorize for me. So in C and C++ you use this hash pragma OMP SIMD, and that says this loop can be vectorized. And in Fortran you use this bang $OMP SIMD, and that tells it the loop is vectorized. And for a lot of compilers, this is not a hint. You're actually telling the compiler this can be vectorized, vectorize it. It doesn't do anything on threads, but it moves it across vector units. And then you can add extra stuff to that. So you can tell it the size of your vector lengths to iterate over. So you can say, I want to, create vectors of length 4 or length 2 or length 8. You can tell it that variables are aligned or not aligned. And then you can do things like private and reduction and collapse. And so these are very much like normal OpenMP variables, but we can do those kind of things. It's also possible to do a SIMD directive for functions. So you can declare a function that can be inserted into SIMD loops. And you can combine that with a for loop. So you can also say, vectorize, split this loop across threads, and then for each thread, if you've got more loop iterations, vectorize it across vector units. So that can be quite a nice portable way of decorating your code and telling the compiler, actually, I know these things can be vectorized here. Even if you're struggling to see that yourself, you can do that kind of thing. So vectorization is quite important for performance, for computational simulation codes. Compilers ideally will do the vectorization for us. Now, I haven't talked about it here. You can write your own vector intrinsics and vector primitives, where effectively you write the instructions for the compiler and put it in the code, and you hard code in the vectorization. We don't generally recommend it because it's not very portable between systems or even between different generations of processors. But it is possible if you're writing some code that really needs to be performant. You can look at the vector intrinsics, and they're not particularly hard to do. But in general, just like with all the other optimizations we've been looking at, what we're trying to do is get the compiler to do the best job possible. And your compiler is a friend here. So what you want to do is look at the compiler output, turn on the optimization output to tell you what optimizations the compiler's doing, find the places it can't vectorize. And you'll have done the profiling first to find out which parts of the code are most expensive. Look in those bits for the loops that can't be vectorized, or the loops that can't be unrolled, or other things the compiler's complaining about, and then see if there are things you can do to those loops to optimize them. Any questions? I appreciate 3:45 on a Friday afternoon. We're all almost done. And I apologize that we've monopolized your time so much with lecturing. There are now a bunch of practicals you can do now. I would skip the vectorization specific practicals myself at the moment and have a look on the exercise sheet. Let me have a look. Let me just share the exercise sheet so we can go through it ourselves. 1 second. Yep. So both of you, let me put the GitHub link up in here. Oh, thank you, Reese. And the vectorization slides should be here now. They weren't earlier on today, but they should definitely be in the repository now. And the updated everything else slides as well. Let me share this anyway. So in this exercise sheet, this is the practical notes sheet in the repository. We had the Cray thing yesterday, which we were vectorizing. You have already hopefully done the OpenMP thing this morning, where we look at the code. Now, There's a number of different things we can do here. There's the compiler optimization exercises that we didn't get round to yesterday. This is the sort of more interesting one to me, or the more useful one, this optimization thing, which is a code which is very similar to a molecular dynamics one here that you did in OpenMP. But it's a code which it's not been parallelized with OpenMP, but it's deliberately been written badly, both in terms of the compiler flags that are used and the code itself. And it runs very slowly. And the idea is for you to try and optimize that using some of the techniques we've looked at. So there are things in there like vectorization, like memory ordering and loop ordering, like combining loops together, getting rid of function calls, playing with the compiler variable flags to get better performance that way, those kind of things. And there's also another practical on bandwidth and NUMA performance with OpenMP, which is quite similar to the first one we ran on using the distributed memory streams, but that can be a useful one to play with. And there's a specific practical on cache blocking, which is quite a nice one to look at and to do some simple cache blocking by hand. So that if you want to get some more hands-on with the cache blocking, that's quite a nice one to do. So the idea now is please do go and have a look at some of these, choose the practical you want to do and have a play around with it. And as I said, I apologies, we've done more lecture and less practicals than we should have done for this course. But you do have access to these accounts for the next month. So you can play with practicals in your own time and just come back and ask questions with me or Mark if you have any. Or indeed, you can get your own code, put it on ARCHER2, do some profiling on it, and look at is there any place we can optimize that there as well. So we're sort of nearly at the end of the session. So as I say, I'll be here to have for anyway. But just before we go, please do ask questions. But I just want to remind you of some of the things I said right at the beginning of the course. Here we go. Let me stop sharing that and share another screen. There's useful resources online for ARCHER2 if you're more interested in that, both the training and the documentation. So this is all from the introduction lecture. If you want to get in touch with me outside this course, then my email address is here, and please do feel free to get in touch. And just remind you that there is also funding for code development as part of this ARCHER2 service. So if you are a code owner or code user and there's things you would like optimized on Archer, then this is a great way of doing it, either getting funding for yourself or somebody at your institute to do code work, or getting somebody like me to work on your code for you. That's a great place to be. So if you have any questions about that, the website's a great place to go, but also just drop me a line and we can chat more about that. And oh, I don't have it up here, do I? I thought I had the slide. I'm sure I had the slide. Well, I don't have a slide. But the feedback, there is a feedback page for this course, which is the thing I really wanted to mention. There is a feedback page for this course. Let me just get it up. And it's always useful for us to have feedback on these courses, particularly at this point where at the beginning of a new service, we're doing a new set of courses. And we're trying to get our training to be sort of well designed for the user community, and also at the moment, given that we're in the middle of COVID and we can't do these things face to face, which is what we'd really like to be doing and how we normally deliver our training, it would be useful for us to know what was good, what was bad, what you changed, what you liked, what you didn't like. Okay, so apologies. What I meant to say is the feedback is on this site here, this Praise site, but it's also on the bottom of the web page for the course, and I'll put it in the chat. But again, it's exactly the same. It's very similar format. And what we want to do is the only one you have to do is is this question at the top here, was it great or was it terrible, or somewhere in between? And you can provide more information if you want, and then you submit it. So that would be useful if you can provide that kind of format.